What if I told you that absolutely everything we know, from the brightest stars to your own body, represents just a tiny part of the universe? Most of the matter that exists out there does not emit light, does not reflect, nor absorb. It is completely invisible. Yet, it is there, exerting a silent but fundamental influence on every galaxy, every cluster, every corner of the cosmos. This enigma, which has intrigued scientists for nearly a century, has a name as mysterious as its own nature: dark matter. Why are scientists convinced that something invisible and seemingly unreachable constitutes almost a third of the entire universe? It's a fascinating paradox. We have never directly seen dark matter, but its gravitational traces are everywhere. If ordinary matter is like the tip of an iceberg peeking out in the cosmic ocean, dark matter would be the gigantic submerged mass holding and shaping everything visible, even though it remains hidden. But how do we know it's there if we have never captured it with our most advanced telescopes? And what does it mean that most of the matter is not of the kind that makes up atoms, planets, and people? Dark matter challenges almost everything we thought we understood about the universe. Its presence was first hinted at by observing strange behaviors in the movement of galaxies and galaxy clusters, movements that the gravity of visible matter could not explain. As if a ghostly force, impossible to see, held galaxies together, preventing them from disintegrating and weaving the large-scale structure of the cosmos. This invisible substance, which represents about 27% of all that exists, remains one of the greatest mysteries of modern science. What is dark matter made of? Are they exotic particles, unknown forces, or perhaps something we cannot even imagine yet? Why, despite all our technological advancements, does it continue to elude our direct observation? Dark matter is the perfect reminder of how much we still do not know about the universe. Every discovery, every clue, every new experiment brings us a little closer to understanding what this fundamental and mysterious component of the cosmos really is. Get ready to dive into one of the greatest mysteries of astronomy: dark matter and the astonishing 27% invisible of the universe. What is dark matter exactly? If everything we see around us, from stars to planets and ourselves, is made of atoms, how can something so fundamental in the universe exist that we cannot directly detect? Dark matter is one of the greatest enigmas of modern science, a form of matter that neither emits, absorbs, nor reflects light, and is therefore completely invisible to all our telescopes and traditional detectors. But if we can't see or touch it, how do we know it's there? The key lies in its gravitational influence. Astronomers have observed that galaxies rotate much faster than they should if they only contained the visible matter they have. If only ordinary matter existed, galaxies would simply crumble as they spin. However, they remain intact thanks to a huge amount of invisible mass that acts like gravitational glue. It's as if you were trying to weigh a box of apples and, upon lifting it, discovered that it is much heavier than it appears. There is something else there, something you can't see but whose presence is undeniable due to the effects it produces. So, why do we call it dark? In reality, the term does not mean that it is black, or that it absorbs light like coal would. It simply refers to our ignorance. It is dark because we do not know what it is made of or how to detect it directly. It does not interact with light or any electromagnetic radiation, unlike ordinary matter. If the universe were a stage, dark matter would be like the cables and structures behind the scenes, holding up the show, but always out of the spotlight. Could dark matter be made of the same atoms that form everything we know? The short answer is no. Ordinary matter, also called baryonic matter, is composed of protons, neutrons, and electrons. Dark matter, on the other hand, must be made up of completely different particles that do not interact with light or electromagnetic forces, making it completely invisible and almost undetectable. It's as if there exists a hidden universe intertwined with ours, but to which we can only access through gravity. In summary, dark matter is the great ghost of the cosmos. We do not see it, we do not touch it, but without it, the universe would not make sense as we know it. Its existence is one of the most fascinating pieces of evidence that there is still much to discover and that, deep down, most of the universe remains a mystery waiting to be solved. Have you ever wondered how much of everything that exists in the universe we can actually see? Although it may seem incredible, all the matter that forms stars, planets, gas clouds, and even interstellar dust represents only a small fraction of the total. Most of the cosmos is made up of something we cannot observe directly, and this is where dark matter comes in. Scientists have calculated that approximately 27% of the universe is composed of this mysterious, invisible substance, far surpassing ordinary matter, which barely reaches 5%. But how is it possible to know this if dark matter does not emit light or energy detectable by our instruments? The answer lies in gravity. Astronomers have observed how galaxies and galaxy clusters behave as if they have much more mass than we can see. It's like trying to weigh a suitcase, and the result is much higher than you expected. You know there's something else inside, even if you can't see it. Thus, by analyzing the movement of galaxies and the way light bends when passing near large concentrations of mass, researchers deduce the presence of that hidden matter. The calculation of 27% is not a simple estimate. It is based on multiple independent observations, such as the study of cosmic microwave background radiation, the large-scale distribution of galaxies, and gravitational lensing patterns. All this evidence points to the same conclusion. Dark matter is essential for maintaining the structure of the universe and explaining the behavior of celestial objects on a large scale. Without it, galaxies simply could not hold together. They would scatter like confetti in space. And what about the rest of the universe? If dark matter represents just over a quarter, what makes up the rest? Surprisingly, about 68% corresponds to dark energy, another great mystery of cosmology. This means that everything we know, everything that has been observed and studied directly, constitutes only a small fraction of the universe. The 27% of dark matter is, then, the key to understanding the functioning and evolution of the cosmos, even though it still remains shrouded in mystery.
If you're enjoying this journey through the universe and want to keep exploring more cosmic mysteries, don't forget to subscribe to the channel and give the video a like. Thank you for being part of this Star Odyssey.
What is dark matter really made of? The short answer is not the same as us. Everything we see around us, from stars and planets to our own bodies, is made up of atoms, which in turn are composed of protons, neutrons, and electrons. We call this matter baryonic matter, and it is responsible for absolutely all the chemistry and physics we know in everyday life. But dark matter does not fit into that scheme. It is not made of atoms. It does not emit, absorb, or reflect light, which means it is completely invisible to traditional telescopes. So why are we so sure it is there? Because it exerts gravity, and its influence is crucial for holding galaxies together and allowing the universe to have the shape we observe. Can dark matter simply be an exotic version of the matter we are familiar with, like non-shining stars, cold planets, or invisible gas clouds? Science has ruled out that possibility. If dark matter were ordinary matter, even if it were hidden, it would inevitably interact with light in some way. For example, a large cloud of cold hydrogen would absorb radiation and could be detected in other wavelengths. However, astronomers have searched and found no sufficient baryonic matter hidden to explain the gravitational effects we observe. Moreover, precise measurements of the early universe, such as the cosmic microwave background, have set clear limits on how much ordinary matter can exist. What makes dark matter so elusive? One of its most fascinating characteristics is that it seems to completely ignore electromagnetic forces. The matter that makes us up, on the other hand, constantly interacts with light and other electrically charged particles. It is that interaction that allows us to see, touch, and experience the world. But dark matter does not participate in these exchanges. It simply passes through the universe and through us as if we did not exist. Some physicists compare it to a ghostly guest at a party. It is present and affects everyone, but no one can see it or talk to it. So how can we ultimately distinguish dark matter from ordinary matter? The key lies in its fundamental interactions. While common matter responds to four fundamental forces of nature: gravity, electromagnetism, strong nuclear force, and weak nuclear force, dark matter only seems to respond to gravity. It does not form atoms, does not generate light, nor does it react with magnetic fields. It is as if 95% of the universe plays under a completely different set of rules, and we are just beginning to decipher it. This radical difference not only makes dark matter one of the greatest enigmas of science, but also redefines our understanding of what matter truly means in the cosmos. Where does that mysterious name come from? Dark matter. Is it some black substance floating in the universe? The answer is much more intriguing. The term dark matter does not refer to a color, nor to something sinister, nor to a shadowy substance. What it really means is unknown matter, or rather, invisible matter. In the early 20th century, astronomers realized that there was something strange about the workings of the cosmos. They observed how galaxies and clusters of galaxies moved, and the numbers simply didn't add up. Something was pulling on the visible matter, but it couldn't be seen with telescopes. It was in 1933 when Swiss astrophysicist Fritz Zwicky first proposed the existence of this invisible matter. By analyzing the movement of galaxies in the Coma cluster, Zwicky noticed that they were moving too fast for the amount of visible matter they contained. He calculated that there must be much more mass than could be accounted for by stars and gas. His solution? He proposed that there existed a Dunkelmaterie, which in German literally means dark matter. In English, the term was translated as dark matter, and thus the greatest mystery of the universe was named. But why dark? The choice of the word was not coincidental. Dark, in this context, means opaque to observation, invisible to our instruments. It's as if we know there is a huge crowd in a stadium, but we can only see those holding flashlights. The rest are there, making noise and changing things, even though they are in complete shadow. Dark matter is that rest that we can only detect by the effect it has on what we can see. Since then, the name has survived decades of research and theories. Interestingly, the term dark matter was adopted by the scientific community without knowing exactly what they were looking for. It serves as a reminder that science sometimes has to name what it doesn't understand in order to study it. Thus, dark matter has evolved from being just a provocative idea to becoming one of the key pieces in understanding how the universe works. Isn't it fascinating that one of the most enigmatic words in astronomy was born simply out of the need to name the invisible? What led astronomers to suspect that there was something invisible in the universe? To answer this question, we must travel back to the 1930s, when a Swiss astrophysicist named Fritz Zwicky wondered why galaxy clusters behaved so strangely. Observing the Coma cluster, Zwicky noticed that the galaxies within it were moving much faster than they should, if only the visible matter exerted the gravitational force that keeps them together. If only the mass of the stars and gas were counted, the galaxies should have simply dispersed, as if you were trying to keep marbles thrown into the air together with just a spider web. Could there be an invisible force at play? Zwicky applied a tool known as the virial theorem, which allows for the calculation of the total mass of a gravitational system based on the velocity of its components. In doing so, he discovered that the observable mass was insufficient to explain the cohesion of the cluster. It was as if the stage were set for a play, but most of the actors were hiding behind the curtain. According to his calculations, the mass needed to prevent the galaxies from escaping was at least 5 times greater than all the visible matter in the cluster. So, where did this extra mass come from? Zwicky called it dark matter because it neither emitted light nor could be directly detected. It was a bold, even controversial proposal that was met with skepticism at the time, but it laid the groundwork for one of the most fascinating questions in modern astronomy. The idea that enormous amounts of matter could be present in the universe without us being able to see it forever changed the way scientists understood the structure and dynamics of the cosmos. Zwicky's finding was the first major hint that the universe might be composed, for the most part, of something completely unknown. Although the evidence at the time was limited and the technology did not allow for precise confirmation, his intuition opened the door to decades of research and a mystery that remains unresolved. What is that invisible matter that holds galaxy clusters together? The answer remains one of science's greatest enigmas, but it all began with the curiosity and ingenuity of Fritz Zwicky, who dared to look beyond the obvious. Why don't galaxies disintegrate while spinning at breakneck speeds? This was one of the big questions that intrigued astronomer Vera Rubin in the 1970s. What she discovered not only forever changed our understanding of the cosmos, but also reinforced the mystery of dark matter. Vera Rubin decided to observe how stars rotate in spiral galaxies, hoping to find that the stars farther from the center moved more slowly, just like the planets in our solar system. But what she found defied all expectations. Rubin's measurements showed something puzzling. The stars at the edges of galaxies spun almost at the same speed as those near the center. How is that possible? Imagine a carousel where the horses on the edge spin just as fast as those in the center. According to the laws of physics and the amount of visible matter, this simply shouldn't happen. If only the matter we can see, stars, planets, gas, and dust existed, galaxies wouldn't have enough gravity to keep those stars on the periphery bound together. They should simply be flung out into space. This anomaly led Rubin to a revolutionary conclusion. There must be a vast amount of invisible matter, a kind of cosmic glue providing the extra gravity needed to keep galaxies cohesive. But where does that force come from? The only viable explanation was that an unknown substance, dark matter, was there, enveloping galaxies with an invisible and massive halo. This matter does not emit light or energy, but its gravitational effect is undeniable. Vera Rubin's work not only provided one of the strongest pieces of evidence for the existence of dark matter, but also showed that most of the mass in galaxies is invisible. Thanks to her perseverance and rigor, we now know that what we see in the universe is just the tip of the iceberg. By studying the movement of stars, Rubin opened a window to the hidden side of the cosmos and forced us to rethink what we thought we knew about the structure and evolution of galaxies. What other secrets lie within that matter we cannot see? The search continues. Have you ever wondered how we know dark matter is there if no one has ever seen it? The answer is intriguing. Dark matter reveals itself solely through its gravitational force. It's like an invisible guest at a party who, although no one can point them out, everyone notices their presence because the dance floor moves strangely. In astronomy, things don't add up if we only count visible matter. Something else, something hidden, pulls on galaxies and distorts space. But it never emits light, nor absorbs, nor reflects any radiation. But what makes us think that this ghostly mass exists? The main clue lies in the behavior of galaxies and galaxy clusters. When astronomers measure the speed at which stars orbit the center of their galaxies, they expect the more distant stars to move slower, just like the planets farther from the Sun. However, what they find is surprising. Those distant stars move as fast as those in the center. What invisible force keeps those stars orbiting without being flung into space? The only logical explanation is that there is a huge amount of mass that we cannot see, exerting its gravity to keep everything together. And is it possible that all that invisible mass is simply gas, dust, or planets that we haven't detected? Calculations show that there isn't enough ordinary matter to explain the observed gravitational force. Even if we added up all the stars, planets, nebulae, and black holes, most of the mass would still be missing. This is where gravity becomes the key tool. It allows us to weigh invisible objects through their effects on what we do see. It's like deducing the existence of a powerful wind by watching trees bend, even though you can't see the air moving. The gravitational evidence for dark matter is not an isolated phenomenon. It repeats at different scales, from individual galaxies to entire clusters. Anomalous movements, the curved paths of light from distant galaxies, and the distribution of matter in the universe only make sense if we accept that most of the matter is not visible, but does have an undeniable gravitational influence. Thus, dark matter remains one of the great mysteries of the cosmos, invisible to all eyes, but impossible to ignore due to the weight of its gravity. How is it possible for something invisible to leave such an evident mark on the cosmos? The answer lies in a fascinating phenomenon: gravitational lenses. According to Einstein's theory of relativity, the presence of mass curves space-time, and this affects the trajectory of light. When light from a distant galaxy passes through a region with a large concentration of mass, like a galaxy cluster, its path is distorted, just as the image behind a glass of water appears warped. But what happens when much of that mass is completely invisible and we only detect it by the way it bends light? Dark matter, although it does not emit or reflect light, does exert gravity. That's why, when astronomers observe images of distant galaxies that appear stretched, duplicated, or forming arcs in the sky, they know that something is acting as a cosmic lens. However, when calculating the visible mass in those regions, they find that most of it is missing. The gravity needed to create those effects can only be explained if there is a large amount of dark matter present. It's like seeing the shadow of an object that you cannot look at directly, but that is undoubtedly there, influencing everything around. Is it possible to measure how much dark matter there is using these gravitational lensing effects? Surprisingly, yes. Scientists can analyze how the light from distant objects is distorted and, with precise calculations, estimate the amount and distribution of matter, both visible and invisible, in the space it traverses. This has allowed the creation of genuine maps of dark matter, revealing that it forms vast invisible structures that connect galaxies and clusters throughout the universe. Without gravitational lenses, these maps would be impossible, and dark matter would remain even more elusive. But here arises another intriguing question. Do gravitational lenses only serve to detect dark matter on large scales? The answer is no. Even on smaller scales, such as within a single galaxy, gravitational lenses can reveal the presence of concentrations of compact dark matter, or structures that visible matter alone cannot explain. These effects, although subtle, help astronomers better understand how dark matter is distributed and how it influences the evolution of galaxies. Thus, gravitational lenses become one of the strongest and most irrefutable pieces of evidence that the universe is filled with something we cannot see, but that is undoubtedly there, leaving its mark on the light of the stars. How do we know how much of our universe is made up of dark matter if we can't even see it? The answer lies in a true cosmic treasure, the cosmic microwave background. This echo of the Big Bang is radiation that has traveled through the universe for nearly 14 billion years. But why is it so important for understanding dark matter? The key is in the tiny temperature variations it contains, like the traces of an ancient crime that reveal details about the original scene. The cosmic microwave background is, in essence, the oldest portrait of the universe. It's like looking at a photograph of the universe when it was just a few 100,000 years old, long before galaxies, stars, or planets existed. What secrets does this primitive image hold? Scientists have discovered that the variations in the intensity of this radiation are not random. They form patterns, like spots on skin, that tell us about the distribution of matter and energy in those early moments. By carefully analyzing these patterns, cosmologists can deduce how much ordinary matter and how much dark matter was spread throughout the young universe. But how does a map of temperatures translate into a cosmic recipe? This is where physics and computational simulations come into play. Models predict how the microwave background should look, depending on the amounts of ordinary matter, dark matter, and dark energy. By comparing these models with actual data obtained from missions like COBE, WMAP, and Planck, scientists adjust the values until they fit perfectly. The result? An astonishing figure. Approximately 1/4 of the universe is dark matter. This method is so precise that the uncertainties are minimal, as if we were trying to weigh an elephant using only the shadow it casts. Why can't we simply measure dark matter directly? Because, unlike ordinary matter, dark matter does not interact with light, so its signature is hidden in the gravitational effects it leaves behind. The cosmic microwave background is a kind of fossil record of those invisible influences. Thanks to this ancient map, we not only know that dark matter exists, but we can also estimate with astonishing precision how much there is, and how it has influenced the evolution of everything we see in the current universe. What does it really mean for dark matter to be cold? It doesn't mean it has a low temperature like ice, but rather refers to the speed of the particles that compose it. In cosmology, when we talk about cold dark matter, we are referring to particles that, from very early in the history of the universe, moved extremely slowly, almost lazily. This may sound curious, but the slowness of these particles has been fundamental for the universe to have the structure we observe today. Why is the speed of these invisible particles so important? If dark matter particles were too fast, as is the case with so-called hot dark matter, they would have traversed the primitive universe without stopping, escaping from the denser regions and preventing gravity from clumping matter to form galaxies and clusters. Cold dark matter, on the other hand, got stuck in the places where density was higher, allowing gravity to do its job and assemble the large cosmic blocks. It's like trying to build a city with bricks that stay put where you place them, instead of using balls that roll and scatter everywhere. This idea of cold dark matter is not just a hypothesis. It is supported by computer simulations and observations of the universe on a large scale. Without the presence of this type of dark matter, simulations show that galaxies and clusters could not have formed in the way they did. And how do we know this? Cosmologists compare the distributions of real galaxies with simulations and find that only the cold dark matter model produces the large filaments and voids that we actually see in the cosmos. Are there specific candidates for cold dark matter particles? Yes, and the most famous of all is the WIMP, a hypothetical massive particle that interacts very weakly with ordinary matter. These particles would be heavy enough and slow enough to fit perfectly into the profile of cold dark matter. However, so far, no one has been able to detect them directly. But the theory remains the favorite because it accurately explains the large-scale structure of the universe. Thanks to cold dark matter, the cosmos looks more like an immense web of galaxies than a homogeneous, shapeless gas. Who would have thought that the secret of the universe's architecture would depend on invisible particles that, moreover, prefer to move slowly? Can dark matter move almost as fast as light? This is the question that gives rise to the concept of hot dark matter. When scientists began to wonder what this mysterious substance is made of, one of the hypotheses was that it could be composed of particles so light and fast that they travel through the universe at speeds close to that of light, like neutrinos. But why would the speed of these particles be important? Because the way they move directly affects how the universe structures itself on a large scale. To understand this, let's think of the early universe as a boiling cosmic soup. If dark matter were made up of extremely fast particles, their frantic movement would have prevented gravity from clumping matter into small seeds, necessary for forming galaxies and clusters. It's like trying to build a sandcastle with grains that fly away before you can stack them. Hot dark matter, in this sense, would tend to smooth out the density differences in the early universe, making it difficult for small and medium structures to form. However, current observations of the cosmos show us something different. We see dwarf galaxies, clusters, and a rich variety of shapes in the early universe. If dark matter were primarily hot, we would expect a much more homogeneous universe, with fewer small galaxies and a large-scale structure very different from what we observe. In fact, models based on hot dark matter fail to reproduce the complexity and distribution of galaxies that we see today. So, is hot dark matter ruled out? Not completely. We know that there are particles like neutrinos that fit into this category, but their contributions to the total dark matter of the universe are minimal. Could there be other similar particles yet to be discovered? It's possible, but the evidence so far suggests that there must be another type of dark matter, slower and heavier, that plays the main role in the formation of cosmic structures. Thus, the idea of hot dark matter, while fascinating, has lost ground to other hypotheses, but it remains a key piece in understanding the complete puzzle of the universe. What if dark matter is neither completely cold nor completely hot? A new question then arises. Is there a middle ground? Thus, the idea of warm dark matter is born, a proposal that sits in the intermediate spectrum between the slow and heavy particles of cold dark matter and the light and fast ones of hot dark matter. Why do scientists consider this alternative? Because some problems in the formation of cosmic structures seem to find a possible solution if this type of dark matter is introduced, neither fast enough to prevent galaxies from clustering, nor slow enough to form only large structures. Warm dark matter is composed of hypothetical particles that, in the primitive universe, moved at intermediate speeds. Imagine a cosmic highway. Cold dark matter would be the heavy trucks moving slowly. Hot dark matter would be motorcycles speeding by. And warm dark matter would be cars traveling at a medium speed, capable of navigating both the city and the highway. This difference in speeds directly affects how and when the first galaxies and clusters form. If dark matter were exclusively cold, we would see a universe with many small galaxies. If it were hot, the small structures simply would not have formed. But what candidates exist for warm dark matter? One of the most mentioned is sterile neutrinos, particles that, unlike normal neutrinos, barely interact with ordinary matter and could have a mass sufficient to fit this warm profile. These sterile neutrinos would be invisible to our current detectors, but they could leave subtle traces in the way galaxies are distributed in the cosmos. This search becomes a complicated puzzle. Scientists analyze the cosmic microwave background and the distribution of galaxies to find clues that fit the theory of warm dark matter. Does warm dark matter solve all mysteries? Not completely. While it helps explain some details about the scarcity of observed dwarf galaxies, there are still doubts about whether it can reproduce all the properties of the universe we know. Moreover, determining the exact mass and properties of the candidate particles remains a huge experimental challenge. Still, the hypothesis of warm dark matter remains alive, inviting science to continue exploring intermediate paths and not to settle for simple answers when the universe insists on being complex. Could this be the balance needed to truly understand what the cosmos is made of? For now, the answer remains one of the most captivating enigmas of modern astrophysics. What kind of particles could compose dark matter? It's one of the most fascinating and challenging questions in modern physics. Although no one has ever seen a dark matter particle, scientists have proposed several candidates that, if they exist, would have properties very different from anything we know. Why is it so difficult to detect them? Because, unlike atoms, these particles do not interact with light or ordinary matter in any significant way. They are literally almost invisible to our senses and current technologies. But that hasn't stopped the scientific community, which has devised clever theories to try to uncover their nature. Among the most studied candidates are the so-called WIMPs, or weakly interacting massive particles. What makes them so special? Imagine a particle with mass, like a proton, but capable of passing through the entire Earth without colliding with anything. WIMPs would be that elusive, and if they exist, they could fill the universe without us hardly noticing. These particles arise from physics models that extend the well-known Standard Model and have been the subject of intense searches in underground laboratories and particle collider experiments. are there more exotic alternatives? Yes, and one of them is axions. These would be extremely light particles, with such little mass that millions could pass through our bodies every second without leaving a trace. Axions were originally proposed to solve a theoretical problem in particle physics, but they turned out to be excellent candidates for dark matter due to their potential abundance and almost ghostly behavior. If axions exist, they could form an invisible sea that envelops the entire cosmos. Not all dark matter candidates have to be elementary particles. Some scientists have proposed the existence of massive and compact astrophysical objects known as machos, which could be brown dwarfs, wandering planets, or primordial black holes. Could dark matter be composed of such large things? Although machos were an attractive hypothesis in the past, current observations suggest they cannot explain most of dark matter, although they could contribute a very small fraction. Beyond these examples, there are even more speculative proposals: sterile neutrinos, supersymmetric particles, and even particles that only interact with each other through unknown forces. What if dark matter is not a single thing, but a mix of several invisible entities? The answer still eludes science, but each new experiment and each theory brings us a little closer to discovering what that mysterious 27% of the universe is made of, which remains for now in the shadows. What if there were particles in the universe so elusive that even though they pass through the Earth by the millions every second, they leave no perceptible trace? Such are WIMPs, or weakly interacting massive particles, the favorite candidate of scientists to explain dark matter. The name says it all. They are particles with considerable mass, but their main characteristic is that they barely interact with ordinary matter. For physics, this is like searching for a needle in a haystack, but with blindfolded eyes and knowing that the needle could be invisible. The theory of WIMPs arises from modern particle physics and is based on the idea that, in the first moments after the Big Bang, the universe was filled with them. Over time, most were annihilated, but a stable fraction remained, wandering through the cosmos. Why have they been the favorites for decades? Because they fit perfectly into cosmological models and solve several problems at once, such as galaxy formation and the distribution of matter in the universe. Moreover, their existence arises from natural extensions of the standard model, such as supersymmetry, which predicts additional particles beyond the known ones. What accounts for their weakly interacting fame? Unlike electrons or protons, WIMPs do not respond to electromagnetic force, meaning they do not emit, absorb, or reflect light. They only feel gravitational forces and, to a lesser extent, the weak nuclear force. This means they can pass through the Earth, our bodies, or even the Sun without being detected. To get an idea, if ordinary matter were like a crowd in a square, WIMPs would be like ghosts that go unnoticed among the people, neither pushing nor brushing against anyone. Despite their shyness, scientists have been developing ultra-sensitive underground experiments for decades to find any sign of their passage. Why such insistence? Because if a WIMP were discovered, it would not only solve the mystery of dark matter, but also open a window to new physics. However, so far, all searches have yielded negative results. Does that mean they do not exist? Not necessarily. Perhaps they are just beyond the reach of our current detectors. Or maybe we need to rethink our understanding of dark matter. The search continues, because in science, every answer leads to new questions. Can a nearly invisible particle, billions of times lighter than an electron, solve one of the greatest mysteries of the universe? Axions, although their name sounds like an anagram invented by a science fiction writer, are one of the most intriguing proposals in the search for dark matter. Why are physicists so interested in these tiny, ethereal particles that could pass through the Earth as if it were fog and leave no trace? The key lies in their nature. Axions, if they exist, would be so light and so non-interacting that they could fill the cosmos without us being able to detect them directly. The story of axions begins with a different problem, completely unrelated to dark matter. an apparent symmetry in particle physics that no one could explain. To solve it, in the 1970s, theorists proposed the existence of a new particle, the axion. But soon, an even bolder idea emerged. What if these axions not only solved that old puzzle, but also were the missing dark matter in the universe? How can something so light exert such influence? The answer lies in the quantity. Axions could be so abundant that, although each weighs almost nothing, together they would add up to a colossal mass. It's like trying to notice the weight of a single snowflake. Insignificant. But if you cover an entire mountain, the effect is gigantic. And how could scientists detect something so elusive? Axions have a fascinating property. In the presence of extremely strong magnetic fields, they could convert into photons, that is, into particles of light. That's why the world's most advanced experiments are trying to listen for that transformation, hoping to catch a faint whisper in the cosmic background noise. It's a challenge comparable to trying to hear a feather fall in the middle of a storm. However, if successful, we would confirm not only the existence of axions, but also a new hidden facet of the universe. Some theorists suggest that if axions exist, they could even form exotic structures, like stars made entirely of axions, or subtly influence the evolution of galaxies. Could axions be the missing piece in the grand cosmic puzzle? If we detect them, we would not only solve the mystery of dark matter, we would also open a door to new laws of physics, and perhaps discover that the universe is even stranger than we imagine. The enigma of axions remains open, challenging scientists to search for the invisible in a cosmos full of secrets. What if dark matter wasn't an exotic particle, but simply objects we already know, yet are too faint or small to be easily detected? This has long been one of the most attractive hypotheses to explain the mystery of dark matter. These potential culprits are called MACOs, which stands for Massive Compact Halo Objects. But what exactly are MACOs, and why did they generate so much interest in the scientific community? MACOs include a variety of celestial bodies that, despite being massive, emit little to no detectable light or radiation. Among them are brown dwarfs, wandering planets, primordial black holes, and even neutron stars that do not shine in the visible spectrum. If you're wondering why they would be candidates for dark matter, think about the difference between a flashlight that is on and one that is off in a dark room. The flashlight that is off is there, but it's invisible to the naked eye. This is how MACOs work. Their mass exerts gravity, but their light does not reach us. During the 1980s and 1990s, experiments were conducted to search for MACOs using a phenomenon called gravitational microlensing. How does this work? When a massive, dark object passes in front of a distant star, its gravity bends the star's light and causes a brief increase in its brightness. It's like a car passing in front of a lighthouse and, for a moment, redirecting the light towards you. Thanks to these studies, astronomers detected some microlensing events, but not in the quantity needed to explain all the dark matter in the universe. So, why did MACOs lose strength as a dominant explanation? Observations showed that these objects can only constitute a small fraction of dark matter. If all the dark gaps in the cosmos were filled with MACOs, we would have seen many more microlensing events, and the behavior of galaxies would be different. Additionally, stellar evolution and nucleosynthesis models predict how much baryonic matter, the kind that forms common atoms, can exist, and MACOs are made precisely of that type of matter. Therefore, although fascinating, MACOs have been relegated to a secondary role in the grand mystery of dark matter. Still, the search for MACOs has not been in vain. It has allowed for a better understanding of the population of dark and exotic objects in our galaxy, and has refined detection techniques for gravitational phenomena. The universe continues to keep its secrets, and although MACOs may not be the protagonists of this story, their investigation has opened new doors to explore the invisible. Could there be other types of compact objects that we have yet to imagine? The cosmos, as always, invites us to keep asking questions. What would happen if dark matter didn't exist? This is one of the most fascinating questions in modern cosmology. Without the invisible presence of dark matter, galaxies as we know them would never have taken shape. In the early universe, after the Big Bang, ordinary matter, that is, the stuff that makes up stars, planets, and ourselves, was so hot and dispersed that it struggled to come together and form structures. So, how was it possible for the first galaxies to appear? The key lies in the silent yet fundamental role of dark matter. Although it does not interact with light, it exerts a powerful gravitational pull. Imagine dark matter as an invisible net that stretches across the cosmos, forming enormous concentrations called halos. These structures were much more efficient at attracting ordinary matter than ordinary matter itself. It was in the gravitational wells created by dark matter that gas and dust could accumulate, cool down, and eventually give rise to the first stars and galaxies. Without these invisible scaffolds, the universe would be a uniform and dull place, lacking the diversity of galaxies we observe today. Why couldn't ordinary matter do this job alone? Because the radiation present in the early moments of the universe pushed ordinary matter away, preventing it from clumping together quickly. Dark matter, on the other hand, is unaffected by radiation. While visible matter was being scattered and resisting the formation of structures, dark matter was already forming large concentrations, serving as gravitational foundations upon which visible matter would later settle. It's as if dark matter built the skeleton of the universe, and ordinary matter only moved in afterward, filling in the gaps. But the influence of dark matter doesn't stop there. Even today, galaxies remain bound together thanks to their halo of dark matter. If we only counted the mass of stars, gas, and dust, galaxies would simply disintegrate due to the speed at which they spin. Dark matter acts like an invisible glue, keeping galaxies cohesive and allowing for the formation of large-scale structures, such as clusters and superclusters of galaxies. Thus, dark matter not only allowed galaxies to be born, but it continues to support and shape them today. Can dark matter influence how galaxies evolve over time? Absolutely. Computer simulations show that the distribution and density of dark matter determine not only where galaxies form, but also how they interact, collide, and grow. In fact, many of the characteristics of galaxies, such as their spiral shapes or the rate at which they form stars, directly depend on the mysterious dark matter. In summary, without dark matter, the universe would be unrecognizable. This invisible component is, in fact, one of the main architects of the cosmos. What do all spiral galaxies, like our Milky Way, have in common? Beyond their majestic arms filled with stars, they all seem to be enveloped by a mysterious, invisible halo, the galactic dark matter halo. But what exactly is this halo, and why are astronomers so sure it exists if no one has ever seen it? The key lies in the speed at which galaxies rotate. If only visible matter existed, the stars furthest from the galactic center should be moving much slower than they actually are. However, observations show that these stars maintain surprisingly high speeds, as if an invisible force is holding them to the galaxy. Could it be that there is something else, something we cannot directly detect with our telescopes, but that exerts a gigantic gravitational influence? This is how the idea of the dark matter halo emerged. A vast spherical cloud made up of unknown particles that surrounds and envelops the galaxy, extending far beyond the disk of stars and gas we can observe. If we imagine the galaxy as a city lit up at night, the halo would be like a huge transparent bubble that completely covers it, providing a kind of gravitational glue that keeps the city together, even when the lights do not reveal everything that is there. But how much larger is this halo compared to the visible galaxy? Calculations indicate that the dark matter halo can be up to 10 times more extensive than the luminous part of the galaxy. That is to say, where the last trace of stars ends, the halo continues, invisible but dominant. In fact, most of the mass of the galaxy resides in this halo and not in the stars, gas, or planets. This disproportion has puzzled scientists for decades because it means that what we see represents only a small fraction of the true galactic structure. And why is this halo so fundamental to the very existence of galaxies? Without it, galaxies as we know them could not exist. Dark matter provides the additional gravity needed to keep gas and stars from dispersing into space, allowing for the formation of stable structures over billions of years. Furthermore, computer simulations show that dark matter halos were essential in the formation of the first galaxies, acting as gravitational seeds in the early universe. Thus, although it remains invisible and undetectable directly, the galactic dark matter halo is the true scaffolding upon which the architecture of the cosmos rests. Did you know that galaxy clusters are the largest natural laboratories in the universe for studying dark matter? Clusters are not just groupings of hundreds or even thousands of galaxies. They are true cosmic titans where gravity keeps everything together. But here comes the unsettling question. How is it possible that those galaxies remain bound to each other when the amount of visible matter, like stars and gas, is not enough to achieve that? The answer lies in the mysterious and dominant ingredient, dark matter. When astronomers began measuring the speed at which individual galaxies move within clusters, they encountered a problem. If only the matter we can see existed, those galaxies should escape the cluster's gravity and disperse into space, as if you were throwing marbles into the air and they never came back down. However, the galaxies remain grouped, spinning at such high speeds that only a much greater amount of hidden mass can explain their cohesion. Where is that invisible mass? It is dark matter, acting as an invisible glue, keeping the galaxies captive in the cluster. Additionally, galaxy clusters contain enormous amounts of hot gas, so hot that it emits X-rays. By analyzing this gas, scientists calculated that it is also insufficient to explain the observed gravitational force. So, what holds that colossal structure together? Once again, the evidence points to dark matter. In fact, in some clusters, more than 80% of the total mass is dark matter, while ordinary matter accounts for only a small fraction. But the story doesn't end there. Galaxy clusters also reveal the existence of dark matter through a fascinating phenomenon called gravitational lensing. When light from distant galaxies passes near a cluster, the cluster's gravity bends that light, creating distorted or multiplied images. By analyzing how much light is deflected, astronomers can map the distribution of mass. And surprisingly, most of that mass is not visible, but corresponds to dark matter. Without this invisible component, galaxy clusters would not only disintegrate, but the universe itself would be radically different from the one we know. What if we had the ability to rewind the universe and watch it evolve from its earliest moments to the present? That is, in essence, what cosmological simulations seek to do. Recreate the history of the cosmos within a supercomputer, starting from the physical laws we know and the matter we assume makes up most of the universe. But a fascinating question arises. How is it possible to reproduce the vastness and complexity of the universe in simple lines of code? The key lies in dark matter. Without it, computational models fail spectacularly to form galaxies and structures like those we observe. When scientists attempt to simulate a universe composed only of visible matter, the results are a scattered cosmos, lacking the intricate web of filaments, clusters, and voids that characterize the real universe. However, by introducing dark matter as the invisible scaffolding upon which ordinary matter assembles, the simulations manage to reproduce the cosmic web, a gigantic spiderweb of matter where galaxies cluster in knots and voids stretch between them. How does this work in practice? Astrophysicists start from the initial conditions shortly after the Big Bang, with slight fluctuations in matter density. They then add the physics of gravity and let the computers do the rest, following the evolution of billions of virtual particles of dark matter and ordinary matter over billions of years. It's like watching an accelerated model of the universe, where dark matter acts as a kind of glue that concentrates ordinary matter, allowing galaxies to be born, grow, and cluster. But can cosmological simulations really predict the universe we see? This is where the comparison between the simulated model and real observations becomes crucial. Surprisingly, the maps generated by the simulations match astonishingly well with the galaxy maps observed through telescopes, both in the distribution of large structures and in the formation of galaxy clusters. This success not only reinforces the existence of dark matter, but also allows scientists to test different hypotheses about its nature. For example, assessing whether dark matter is cold, hot, or warm, and seeing which one best reproduces the current universe. In summary, cosmological simulations have revolutionized our understanding of the cosmos. They are like virtual laboratories where astrophysicists can experiment with the rules and ingredients of the universe. Thanks to them, we have learned that without dark matter, the universe simply would not be as we know it. Every time a simulation successfully predicts what we see in the sky, it's as if dark matter, still invisible, leaves us a clear message. Its imprint is etched in the architecture of the cosmos. What role does dark matter play in the expansion of the universe? Many might think that, since it represents more than a quarter of the cosmos, dark matter is directly responsible for the universe expanding faster and faster. However, the reality is more intriguing. Dark matter, unlike dark energy, does not push space outward. It actually acts like a kind of cosmic glue, attracting matter and slowing down the expansion due to its gravity. So why then, if it is there slowing things down, does the universe continue to accelerate its expansion? The answer lies in the competition between dark matter and dark energy, two fundamental ingredients with opposite effects. For billions of years, dark matter helped shape the structure of the universe, allowing galaxies and clusters to form and remain bound together. Its gravity countered the natural tendency of space to expand since the Big Bang. It's as if the universe were a loaf of bread rising in the oven. Dark matter, with its gravity, would be like a net trying to prevent the dough from overflowing, while dark energy pushes for the dough to grow more and more. But as the universe expands and dark matter disperses, its gravitational influence decreases compared to the constant push of dark energy. This leads to a fascinating question. When did dark energy start to win this cosmic battle? Astronomers have calculated that about 5 billion years ago, dark energy surpassed the combined gravitational influence of all matter, including dark matter, and the expansion began to accelerate. Before that moment, the gravity of dark matter was strong enough to slow down the expansion, but dark energy, with its mysterious repulsive effect, ultimately came to dominate the fate of the cosmos. Does this mean that dark matter has lost all relevance in the evolution of the universe? Not at all. Although it can no longer slow down the accelerated expansion, dark matter remains essential for understanding how galaxies are distributed and how cosmic structures are held together. Without its presence, the universe would be a much emptier and more chaotic place. Thus, dark matter and the expansion of the universe are deeply intertwined, starring in a cosmic dance of attraction and repulsion that defines the history and future of everything that exists. Did you know that dark matter and dark energy are not the same thing, even though their names sound almost identical? It's one of the most common confusions in cosmology, and yet both entities represent completely different mysteries of the universe. If dark matter is like an invisible ghost shaping the gravity of galaxies and clusters, dark energy is more like an enigmatic force that seems to be inflating the very fabric of the cosmos. Why is it so important to distinguish between them? Dark matter acts like an invisible glue, holding galaxies and large cosmic structures together. It doesn't emit light, doesn't absorb radiation, and doesn't interact with anything except through gravity. It's as if you were on a dance floor, feeling someone take your hand and guide you, but you never see who is accompanying you. In contrast, dark energy operates in the opposite way. It doesn't keep anything together, but rather pushes everything apart. It is responsible for the acceleration of the universe's expansion, as if someone were pressing the accelerator without us knowing how or why. Have you ever wondered why astronomers are so sure that both exist, if neither can be seen directly? Dark matter reveals its presence through the gravitational effects it causes. Galaxies spinning too fast for the amount of visible matter. Galaxy clusters that don't disintegrate despite how little we see. Dark energy, on the other hand, is inferred by observing that, on a large scale, galaxies are moving away from each other at an increasing speed. If dark matter slows down the expansion with its gravity, dark energy acts like an anti-gravitational engine that accelerates it. In terms of proportions, the difference is also staggering. Approximately 1/4 of the cosmos is dark matter, while nearly 7/10 corresponds to dark energy. It's surprising to think that everything we see, ordinary matter, barely adds up to a minimal fraction of the total. Thus, although they share a surname, dark matter and dark energy are not close relatives. One shapes the structure of the universe, the other determines its final fate. Understanding the difference between the two is fundamental to deciphering the greatest puzzle of modern physics: what the universe really is and what it is made of. What if dark matter not only interacted with gravity, but also with itself, as if it had a secret social life in the universe? This intriguing possibility has given rise to the hypothesis of self-interacting dark matter. The idea is simple, yet revolutionary. Instead of being completely indifferent to one another, dark matter particles could collide, repel, or attract each other through unknown forces. Why consider something like this? Because there are astronomical observations that are not fully explained if we treat dark matter as a crowd of solitary particles, with no contact between them. For example, when studying dwarf galaxies and the centers of larger galaxies, astronomers have found that the distribution of dark matter is more uniform than traditional models predict. Wouldn't it be logical that if dark matter interacts with itself, these internal collisions and pushes would smooth out the galactic cores, creating less dense regions? It's as if instead of a silent and dispersed crowd, dark matter formed a kind of moving multitude, where pushes and nudges affect how it clusters. Could self-interacting dark matter solve other cosmic mysteries? During collisions of galaxy clusters, such as in the famous bullet cluster, it is observed that dark matter seems to separate from visible matter. One possible explanation is that by interacting with each other, part of the dark matter slows down or is distributed differently, generating more complex patterns than gravity alone would allow. This hypothesis could also explain some oddities in the formation of small galaxies and the absence of certain expected structures in classical models. However, self-interacting dark matter remains a developing idea. Scientists are searching for signals of these possible interactions in large simulations and in the observation of cosmic structures. What kind of force could exist between particles that neither emit, absorb, nor reflect light? No one knows for sure. But if this hypothesis turns out to be correct, it could open a completely new window on the nature of dark matter and, by extension, on the deeper rules that govern the universe. For now, self-interacting dark matter is one of the most fascinating paths in the quest to understand the invisible. What if dark matter were passing right through you at this very moment, without you being able to feel or see it? That's exactly what scientists suspect, and that's why they've devised astonishingly clever experiments to try to detect it directly. But how do you search for something as elusive as dark matter, which doesn't emit light or respond to any known forces except gravity? The answer lies in patience, precision, and the hope of capturing a tiny interaction in a sea of noise. The challenge is monumental. Dark matter, if made up of particles like WIMPs, interacts so weakly with ordinary matter that it can pass through the entire Earth without a trace. To try to catch it, scientists have built underground laboratories, protected beneath kilometers of rock. Why so deep underground? To isolate the detectors from the constant bombardment of cosmic rays and particles that could confuse the results. It's like trying to hear the faint whisper of a feather in the middle of a rock concert. You need to turn down the background noise as much as possible. In these laboratories, extremely sensitive detectors are used, some made of ultra-pure liquid xenon, others of special crystals, or germanium cooled to nearly absolute zero. The hope is that at some point, a dark matter particle will strike a nucleus of these materials and produce a detectable signal, a slight flash of light, a tiny vibration, or a minuscule release of heat. But detecting that event is like searching for a needle in a haystack the size of the universe. The detectors must operate for years, waiting for that rare hit that could forever change our understanding of the cosmos. And what happens if we never see a signal? Does that mean dark matter doesn't exist? Not necessarily. Every experiment that finds nothing narrows down the possible characteristics of dark matter. It rules out certain types of particles, constrains its mass, limits its likelihood of interacting. It's like exploring a dark cave with a flashlight. Even if we don't see the monster, every illuminated corner tells us something about where it might be hiding. Thus, the direct search for dark matter is one of the greatest bets of modern science, a mix of patience, advanced technology, and humanity's eternal curiosity to uncover the invisible. Is it possible to detect something we have never seen, touched, or measured directly? That is the question guiding the indirect search for dark matter. If these mysterious particles do not emit, absorb, or reflect light, how could scientists even suspect their existence? The answer lies in looking for the traces they leave behind, like an invisible thief who, although no one has seen him, leaves clear signs of his presence. One of the most intriguing methods involves searching for signals from the annihilation or decay of dark matter particles. What does this mean? If dark matter is made up of certain particles, it is possible that when two of them meet, they annihilate each other and produce other known particles, such as gamma rays, positrons, or neutrinos. Space telescopes and ground-based detectors scan the cosmos for these subtle flashes of energy. But how can we distinguish a signal caused by dark matter from all the other sources in the universe? That is one of the great challenges. The cosmos is filled with violent and mysterious phenomena that also generate these particles. In some cases, astronomers focus their attention on regions of space where dark matter is expected to be particularly abundant, such as the center of our galaxy or in nearby small satellite galaxies. If an excess of gamma rays or positrons is detected in those areas that cannot be explained by known sources, suspicion arises. Are we witnessing the indirect trace of dark matter? However, interpretation is never straightforward. The universe is a chaotic natural laboratory, and distinguishing between the ordinary and the extraordinary requires caution and patience. What if dark matter interacts so weakly that its particles simply decay over time, emitting subtle signals? Here too, the search is indirect. Researchers look for anomalous patterns in the data, such as an unexpected excess of neutrinos or a peculiar distribution of cosmic rays. It's like trying to hear a whisper in the midst of a storm. So far, none of these searches have provided a definitive answer, but each clue, each anomaly, brings science a little closer to the moment when, finally, the mystery of dark matter will no longer be invisible. What role does the Large Hadron Collider play in the mystery of dark matter? At first glance, this gigantic particle accelerator, buried beneath the border between Switzerland and France, might seem designed solely to study the fundamental building blocks of visible matter. However, one of its most ambitious goals is precisely to search for clues of that other hidden universe, dark matter. Physicists know that ordinary matter, the stuff that you, I, the stars, and the planets are made of, represents only a small fraction of the cosmos. So why not try to create or detect dark matter particles in the most powerful laboratory in the world? The Large Hadron Collider functions like a kind of mini Big Bang machine. By colliding protons at speeds close to that of light, it recreates extreme conditions similar to those of the early universe. But how could this reveal dark matter? If there is a particle responsible for that invisible matter, it could be produced in one of these collisions. The challenge is that dark matter, by its very nature, does not easily interact with detectors. It's like trying to hear the whisper of a leaf in the midst of a storm. That's why scientists are indirectly searching for its trace. If, after a collision, energy or momentum is missing, it's possible that an invisible particle, perhaps dark matter, has escaped undetected? And what kind of particles do they expect to find? One of the major candidates is the so-called WIMPs, weakly interacting massive particles. The Large Hadron Collider could, in theory, create them if they truly exist. If this were to happen, it would be a revolutionary discovery, as it would allow for direct study of their properties and a better understanding of how they behave in the universe. However, so far, despite millions of collisions and years of analysis, no conclusive signal of these particles has been found. Does this mean that dark matter does not exist? Not necessarily. It could be that the particles are even more elusive, lighter, or that they interact in a completely unexpected way. The Large Hadron Collider remains one of the most promising tools in the search for answers. Each new energy reached, each update in its detectors, opens the door to possibilities that have not been explored before. Particle physics is, in many ways, feeling around in the dark. But every result, even those that find nothing, is a crucial step in ruling out theories and guiding efforts toward new paths. Thus, the race to discover the identity of dark matter remains open, and the world's largest particle accelerator continues to push the boundaries of our knowledge. What makes dark matter so mysterious? If it makes up more than a quarter of the universe, why can't we see or touch it? The secret lies in how it interacts with light and the rest of matter. Everything we know, from an apple to a star, shines or reflects light because its particles interact with electromagnetism. But dark matter seems completely indifferent to light. It neither emits, absorbs, nor reflects it. It's as if there exists a type of matter that traverses the cosmos like an invisible ghost, oblivious to the eyes and the most powerful optical instruments. Is it possible that dark matter is made of some ultra-exotic material, so different from everything we know that even our detectors can't perceive it? Scientists think the key lies in the fundamental forces of nature. Ordinary matter interacts through four forces: electromagnetism, gravity, strong nuclear force, and weak nuclear force. Dark matter, however, seems to ignore three of them and only responds to gravity. Imagine trying to find someone in a completely dark room, unable to use sight, hearing, touch, or smell, and only knowing they're there because you feel the floor slightly sink under their weight. That's how limited our ability is to detect dark matter. Couldn't we build a more powerful telescope to see it? The answer is that no matter how sophisticated the instrument is, if dark matter doesn't interact with light at all, it remains completely invisible to any detector based on the electromagnetic spectrum. It's like trying to photograph the wind. You can see its effect on the leaves, but you never capture the wind itself. That's why all the information we have about dark matter comes from observing its gravitational effects, such as the movement of galaxies, or the way it bends light passing near large mass accumulations. Is there any hope that one day we might see it directly? Some scientists believe there could be very weak, yet undiscovered interactions that would allow us to detect it with extremely sensitive experiments. However, so far, dark matter remains invisible, the great enigma of modern astronomy. Its existence challenges our ideas about what it means to see in the universe. It forces us to think of a cosmos where most of what exists cannot be observed in the traditional way, but only intuited through its mysterious traces. Why is dark matter so important for particle physics? The reason is simple. What we know about the universe, what we see and measure, barely scratches the surface. Dark matter represents one of the greatest unknowns in modern physics, as it does not fit into the standard model, the theory that describes known particles and forces. If the standard model were a puzzle, dark matter would be the missing piece, and without it, the picture makes no sense. Scientists believe that to truly understand what dark matter is made of, we must venture into unknown territories, where new particles and forces may be waiting to be discovered. Is it possible that there are invisible particles, completely unrelated to everything we have detected so far? Most physicists think so. dark matter would be a type of elementary particle that does not interact with light or other forces, except for gravity. This raises a fascinating question. Is there a hidden zoo of particles that we have never seen, but that hold the universe together? Underground laboratories and particle accelerators tirelessly search for signals of these elusive particles. The discovery of just one of them could revolutionize particle physics as we know it, opening the door to a new branch of science. The challenge is so great that it has inspired theories that go far beyond the conventional. For example, some scientists propose the existence of extra dimensions or new forces of nature to explain why dark matter is so difficult to detect. What if dark matter interacts with itself through a completely unknown force? Or could it be that there are entire families of particles, like the famous WIMPs or axions, waiting to be discovered? Each hypothesis implies rethinking the foundations of physics, and each negative experiment brings us closer to what is really out there. The search for dark matter is, in fact, a quest for the limits of our knowledge. If we come to discover what particles compose it, we will not only solve a cosmic mystery, but could also find new fundamental laws of nature. The universe could be full of surprises, and dark matter is the most intriguing clue we have to explore the unknown in particle physics. What other wonders await us once we decipher this enigma? What if dark matter didn't exist? What if, in reality, what's failing is our understanding of how gravity works on a large scale? This is the bold question that led some scientists to propose the MOND hypothesis, which stands for Modified Newtonian Dynamics. MOND challenges one of the most fundamental ideas in physics, that the law of gravity we know applies equally throughout the universe. Could it be that, when observing the movement of stars in galaxies, we are not seeing the effect of invisible matter, but rather a signal that gravity behaves differently when it is extremely weak? The MOND hypothesis was proposed in 1983 by physicist Mordechai Milgram. He noticed that, in the outskirts of galaxies, stars move faster than the gravity of visible matter would allow. Instead of assuming there is something invisible that increases gravity, Milgram suggested that Newton's own law might need an adjustment when accelerations are very low. It's as if gravity has a turbo version that only activates in the farthest regions of galaxies, allowing stars to keep spinning at high speeds without the need for additional matter. Does this idea make sense? Surprisingly, MOND can explain the movement of stars in many galaxies without resorting to dark matter. In fact, if one applies Milgram's modified formula, the results match quite well with observations in certain cases. It's like adjusting a cake recipe because, at high altitude, the oven heats differently. The classic recipe doesn't always yield the same results everywhere, and perhaps the universe has its own local rules for gravity. Moreover, MOND accurately predicts the relationship between the visible mass of a galaxy and the rotation speed of its stars, a fact that has fascinated several astronomers. However, MOND also faces serious challenges. While it works well for individual galaxies, it fails to explain phenomena on larger scales, such as the dynamics of galaxy clusters or the cosmic microwave background. It also doesn't fully align with Einstein's general theory of relativity. For some, this is a sign that MOND is merely a partial approximation, while others believe it could be the tip of the iceberg toward a still unknown physics. Are we facing a clue that fundamental laws require a revision, or just a temporary patch? To this day, most of the scientific community still considers dark matter to be the most solid explanation for the observed phenomena. But MOND remains an intriguing alternative. Its very existence reminds us that science progresses by questioning its own foundations. What if we still haven't discovered all the rules of the cosmos? The MOND hypothesis is, ultimately, a window into the possibility that the universe holds even deeper secrets than we imagine. What if everything we know about dark matter is actually the result of a measurement error? This question has troubled scientists for decades. In science, discovering something as mysterious as dark matter always involves asking, what if our instruments are deceiving us? Astronomers have devoted considerable effort to searching for possible flaws in the observations that led to the suspicion of its existence. For example, the first hints of dark matter emerged when it was noticed that stars at the edges of galaxies move much faster than expected. Could there be an error in how we measure those speeds, or perhaps in how we interpret the light from distant stars? Think about trying to weigh a person using a miscalibrated scale. If the scale reads higher than it should, you might incorrectly conclude that the person is heavier. In this way, scientists have wondered if their cosmological scales, the techniques and models used to calculate the masses of galaxies and clusters, might be misaligned. Perhaps we have underestimated the amount of visible matter, or maybe there is some unknown aspect of how light behaves as it travels through space. It has even been considered whether interstellar dust could be absorbing some of the light, hiding matter that is actually there and that we simply do not see. The methods used to measure cosmic distances and the velocities of celestial objects have also been scrutinized. Is it possible that the observed speeds are affected by gravitational effects that we do not fully understand yet? If the physics of gravity were different on a large scale, the calculations of mass and galactic motion might need correction. Some astronomers have explored the possibility that the very law of gravity, as we know it, might require adjustments when applied to enormous distances, rather than resorting to the existence of invisible matter. This idea has given rise to alternative theories, such as modified Newtonian dynamics. However, after countless checks, the possible measurement errors have not fully explained what is observed. The evidence for dark matter comes from various sources and techniques, such as the analysis of galactic rotation, the observation of gravitational lenses, and the study of cosmic background radiation. All point in the same direction. There is something beyond what we can see. While science never rules out the possibility of errors, so far, no alternative explanation based solely on measurement failures has been able to eliminate the need to postulate the existence of dark matter. Scientific doubt is healthy and essential, but each review has reinforced the idea that the universe hides much more than our eyes can capture. What happens when two gigantic galaxies collide in space? Do they disappear in a cosmic explosion or simply pass through each other like ghosts? Galaxy collisions are one of the most violent and spectacular events in the universe, but they also provide some of the most clues about the mysterious dark matter. An emblematic case is the so-called bullet cluster, where two galaxy clusters collide at astonishing speeds. This event is key to understanding how dark matter behaves because it reveals a phenomenon that cannot be explained solely by visible matter. When observing collisions like the bullet cluster, astronomers noticed something puzzling. Most of the visible matter, that is, the stars and hot gas, behaved one way, while another invisible mass seemed to move on unaffected. How do we know this? When two galaxy clusters collide, the hot gas they contain interacts, slows down, and heats up even more, emitting X-rays. However, the gravitational effect, measured by the phenomenon of gravitational lensing, is concentrated in areas where the gas is no longer present, only invisible matter remains. This suggests that most of the mass does not slow down, does not interact, and does not heat up. It simply passes through the collision as if nothing happened. Why is this so important for dark matter? If all the mass of a cluster were in the gas and stars, the center of gravity of the collision should coincide with where the hot gas is. However, studies show that gravity is stronger where there is hardly any visible matter left. It's as if on a highway, you crash two cotton trucks. And in the end, most of the weight continued moving along invisible paths. The only coherent explanation is that there is a large amount of matter that does not interact electromagnetically, dark matter. Does this mean that dark matter does not feel the collisions? Exactly. Unlike normal matter, which collides, slows down, and emits light, dark matter hardly interacts with itself or with other particles, allowing it to pass through the chaos of a galactic collision unscathed. The bullet cluster is not the only case. There are other systems, like MACS J0025, that show similar patterns. These observations have become one of the most direct and convincing pieces of evidence for the existence of dark matter because they rule out alternative explanations, such as measurement errors or theories that modify gravity. In short, galaxy collisions are like cosmic laboratories that show us, in an almost irrefutable way, that there is something more out there, invisible but with a fundamental weight in the universe. What would the universe be without dark matter? To understand the magnitude of its role, one must think about the early stages of the cosmos, when everything was a hot, dense soup of particles. How is it possible that this chaotic mix organized itself into galaxies, clusters, and the gigantic structures we see today? The answer is surprising. Dark matter was the invisible skeleton that allowed ordinary matter to clump together. Without it, the universe would be a much more uniform and boring place, with no galaxies or stars, just a diffuse cloud of atoms floating for eternity. How does dark matter influence cosmic evolution? Although no one has ever seen a dark matter particle, its gravity acts like a network of highways in space. In the first hundreds of thousands of years, ordinary matter was too hot and energetic to form structures, while dark matter, insensitive to radiation, was already starting to clump under the influence of gravity. These clumps acted as gravitational wells that attracted visible matter, allowing the first galaxies and stars to be born millions of years later. Have you ever wondered why the universe has that appearance of a cosmic web, with filaments, voids, and nodes where galaxies concentrate? The key lies in dark matter. Computer simulations show that when modeling the universe with only visible matter, these complex and branched structures do not appear. It is dark matter that, through its gravitational attraction, guides the formation of these massive filaments and defines the large-scale landscape. It's as if dark matter drew a secret map, and ordinary matter simply followed it. But the role of dark matter did not end with the birth of the first galaxies. Over billions of years, it has continued to act as the cosmic glue that holds galaxies together and prevents them from dispersing due to the expansion of the universe. Without its influence, many galaxies would have disintegrated, and large-scale structures would not exist as we observe them. Thus, cosmic evolution, from the original chaos to the complex tapestry of galaxies surrounding us, has been largely directed by this mysterious substance. Dark matter is, in essence, the silent architect of the universe's history. Where does dark matter hide in the universe? Although it is invisible, its distribution is not random. Astronomers have discovered that dark matter clusters into large structures, weaving a kind of cosmic web that spans the entire cosmos. This web is made up of colossal filaments that connect clusters of galaxies, leaving vast voids between them. In fact, dark matter acts as the invisible skeleton of the universe, guiding the formation and arrangement of galaxies and large-scale structures. Is it distributed evenly? Not at all. Dark matter is much denser in regions where galaxy clusters are found, and much less present in intergalactic voids. You can imagine it as a gigantic three-dimensional spider web. The nodes, where the strands cross, are the places where galaxies and clusters group together, while the strands themselves are formed by currents of dark matter that link these concentrations. The voids, on the other hand, are regions where the presence of this matter is minimal, almost non-existent. How do we know all this if we can't see it? Scientists have mapped the distribution of dark matter by analyzing the movement of galaxies and the effect of gravitational lensing. When the light from distant galaxies passes near large concentrations of dark matter, its path bends, revealing the presence of that invisible mass. By studying thousands of these distortions, we can reconstruct the map of dark matter in the universe, discovering that it forms true filaments and nodes, very similar to the predictions of computational simulations. The scale of this distribution challenges the imagination. The filaments of dark matter can stretch for hundreds of millions of light years, while the clusters of galaxies that form at their intersections can contain thousands of galaxies. This structure not only determines where galaxies form, but also how they evolve over time. Thus, although we cannot see dark matter, its distribution is fundamental to understanding the architecture and history of the universe. What do a spider web and the universe have in common? It may sound strange, but the comparison is more accurate than you might think. The cosmos, at its largest scale, is woven by enormous filamentous structures known as the cosmic web. These formations are not made of silk, but of matter, galaxies, and, above all, an invisible substance, dark matter. Why does the universe adopt this pattern of filaments and voids? The answer takes us back to the first moments after the Big Bang and the mysterious influence of dark matter. Dark matter acts as the invisible scaffolding upon which the universe is built. If we could see this matter directly, we would observe a three-dimensional network of gigantic filaments connecting clusters of galaxies to each other. In these filaments, the gravity of dark matter attracts and concentrates ordinary matter, allowing for the formation of galaxies and galactic groups. The spaces between the filaments, known as cosmic voids, are almost devoid of matter, creating an extreme contrast in the distribution of mass on a universal scale. How do we know this if we cannot see dark matter? Computer simulations and maps of observed galaxies confirm that these structures can only be explained if most of the mass is composed of dark matter. To what extent is dark matter dominant in these filaments? It is estimated that more than 90% of the mass in filamentous structures corresponds to this invisible matter. Ordinary matter, that is, the matter that forms stars, planets, and ourselves, represents merely the visible decoration on the main threads of the cosmic web. It's as if dark matter is the hidden highway and galaxies are the illuminated cars that only give us a glimpse of the path they are taking. This web, spanning hundreds of millions of light years, defines the architecture of the universe on a large scale and determines where new galactic clusters can form. And how do these filaments form? It all begins with small fluctuations in density after the Big Bang. Dark matter, by its nature, starts to clump together under its own gravity, dragging visible matter along with it. Over billions of years, these regions of higher density grow and connect, generating the enormous filaments that intertwine the universe. Without dark matter, this cosmic skeleton simply would not exist. The universe would be a much more homogeneous place, lacking large structures. The existence of cosmic filaments is therefore one of the most impressive pieces of evidence for the fundamental role of dark matter in the design of the universe. What does it take to search for something we cannot see, touch, or smell? The answer is ingenuity, patience, and of course, extremely sensitive instruments. Although dark matter is invisible, astronomers have developed observatories and telescopes that allow them to trace its footprints, like cosmic detectives searching for clues on the grand stage of the universe. But what are these privileged eyes that help us follow the trail of the invisible? One of the most iconic observatories is the Hubble Space Telescope. Although it was not specifically designed to detect dark matter, its ability to observe distant galaxies and study the phenomenon of gravitational lensing has been crucial. When dark matter bends the light from distant galaxies, Hubble can capture that effect, allowing us to map the distribution of invisible matter. It's like seeing the shadow of an object that we can never directly illuminate, but which reveals its presence by the way it distorts the surroundings. The Fermi Space Telescope, specialized in gamma-ray detection, is another key player in this search. Scientists scan the sky for unusual gamma-ray signals that could result from the annihilation or decay of dark matter particles. If dark matter interacts with itself, as some models predict, it could emit bursts of energy that Fermi would be able to detect. Thus, Fermi acts as a hunter of cosmic ghosts, alert to any fleeting trace that reveals the activity of the hidden. On Earth, there are also observatories dedicated to dark matter. The Xenon experiment, located in the underground laboratories of Gran Sasso in Italy, uses enormous tanks of liquid xenon to try to capture the direct impact of dark matter particles passing through our planet. These underground experiments are shielded from cosmic noise using tons of rock, as if they were trying to listen for the soft murmur of a conversation amidst a deafening concert. Finally, there is another type of telescope that does not look to the sky for light, but for distortions in the structure of the universe itself. Microwave telescopes, like the Planck satellite. This observatory has mapped the cosmic microwave background with high precision, the fossil radiation from the Big Bang, revealing patterns that can only be explained if there is a large amount of dark matter. It's like reading the wrinkles of a sheet to deduce what is underneath, even though we can never see it directly. Each of these observatories and telescopes contributes a fundamental piece to the puzzle. The hunt for dark matter does not rely on a single instrument, but on a symphony of technologies, methods, and international collaborations. Although we have not yet managed to observe dark matter directly, these scientific giants have brought us much closer to unveiling one of the greatest mysteries of the cosmos. Are we about to discover what dark matter is? This is one of the most exciting questions in modern astrophysics, and the answer could forever change our understanding of the universe. Although dark matter remains invisible and elusive, the next generation of experiments and observatories promises to bring us closer than ever to unveiling its true nature. How do scientists plan to solve this cosmic enigma? One of the most ambitious strategies is the construction of even more sensitive underground detectors, such as the Xenon NT experiment in Italy and LUX Zeppelin in the United States. These laboratories, buried kilometers underground to avoid interference from cosmic radiation, are searching for tiny signals that could indicate the presence of dark matter particles passing through the Earth. It's like trying to catch the flutter of a butterfly in the middle of a hurricane. Every small flash of energy could be the key to identifying the elusive constituents of this mysterious matter. But what if dark matter reveals its existence not through direct impacts, but through its secondary effects? Astronomers are on the lookout for signals in space that could betray the annihilation or decay of dark matter particles. Space telescopes like Fermi-LAT or the future Cherenkov Gamma Ray Observatory are scrutinizing the cosmos for excess gamma rays or neutrinos, hoping to find patterns unexplained by known sources. Like cosmic detectives, scientists are tracking clues that could be hidden in the most unsuspected places in the universe. What if the solution lies in particle collisions? The Large Hadron Collider in Europe is still in the race to generate unknown particles that could match the theoretical properties of dark matter. Soon, new, even more powerful accelerators could open windows to dimensions and particles never seen before, testing the boldest theories of contemporary physics. Additionally, space missions like Euclid and the Nancy Grace Roman Space Telescope will seek to map the large-scale distribution of dark matter more accurately, helping to rule out models and refine our predictions about how this invisible component of the cosmos behaves. Could there be even greater surprises? Some physicists propose radical theories, such as the possibility that dark matter interacts with itself through new forces, or that multiple types of dark matter coexist in the universe. The coming years could bring unexpected discoveries that challenge even the most firmly established ideas. Research on dark matter stands at the frontier of science, and each experiment, each mission, and each new observation brings us step by step closer to one of the greatest revelations in human history, understanding what our universe is truly made of. Did you know that despite dark matter accounting for more than a quarter of the universe, there may be entire galaxies with almost none of it? Recently, astronomers have detected some ultra-diffuse galaxies where the presence of dark matter seems to be very low or even non-existent. How can this be possible if dark matter is essential for holding galaxies together? This enigma has led scientists to reconsider some of their hypotheses and seek alternative explanations, such as past interactions with other galaxies or unconventional formation mechanisms. An astonishing fact is that dark matter could literally be passing through you right now. It is estimated that trillions of dark matter particles pass through our bodies every second without leaving a trace or interacting with any of our atoms. If dark matter were a breeze, we would be like ghosts to it. This happens because it does not couple with electromagnetic forces, making it completely transparent and undetectable to our senses and most scientific instruments. Can dark matter form complex structures like planets or even life? As far as we know, the answer is no. Unlike ordinary matter, dark matter cannot easily lose energy or cool down in the way atoms do, which prevents it from clumping together to form compact objects like stars or planets. For this reason, although dark matter is much more abundant, everything we see and know, including ourselves, is made of that scarce 5% of baryonic matter in the universe. An even more intriguing curiosity is that, in theory, dark matter could be forming tiny clusters of its own, known as subhalos, that float around galaxies like ours. Some scientists believe that these subhalos could have enough gravity to deflect stars or even produce observable effects on the movements of objects within the galaxy. However, so far, detecting these subhalos is a real challenge, as their only footprint would be the gravitational influence they exert on their surroundings. Finally, there is the possibility that dark matter is not a single thing, but rather a mixture of different types of still unknown particles. This scenario is akin to opening a box and finding not just one surprise, but a complete set of mysteries. Thus, dark matter could be the tip of a much more complex iceberg, waiting to be unveiled by future generations of curious and bold scientists. What does it mean for us that most of the universe is invisible and to some extent unknowable? Dark matter poses one of the deepest philosophical questions of modern science. Is it possible to know reality in its entirety, or are we doomed to perceive only a fraction of what exists? As if the cosmos were showing us only its facade, dark matter is the constant reminder that the essential may remain hidden from our senses and our technology, no matter how advanced they are. Can we trust what we see if we know that more than 2/3 of the universe escapes our direct observation? This uncertainty challenges the classical idea that knowledge always progresses toward complete understanding. Just as an iceberg shows only a small part of its mass above the surface, visible matter would be merely the tip, while the majority, dark matter, remains submerged and unreachable for direct observation. This forces us to wonder if the reality we experience is just a shadow of a much more complex and mysterious structure. The existence of dark matter also questions the notion that the universe is a place tailored for our understanding. What if the laws we have formulated only describe a small window, and the rest of the universe operates under principles we have yet to imagine? In a sense, the mystery of dark matter is an invitation to intellectual humility. Each discovery reveals new frontiers, and every certainty seems surrounded by a vast ocean of unknowns. To what extent are our perception and our theories limited by the instruments and concepts we have at our disposal? Finally, dark matter confronts us with a fascinating paradox. Its existence is inferred, not because we see it, but by the effect it has on what we can see. Can something be as real as the invisible? This question echoes ancient philosophical debates about the nature of reality and perception. If the universe is mostly composed of something that escapes our sight, what does that say about the place we occupy in it and the way we construct our knowledge? Dark matter, in that sense, is a mirror that reflects both the vastness of the cosmos and the limits of our understanding, inviting us to keep asking questions, even if we never find all the answers. Why is the universe mostly made up of something we cannot see or touch? How is it possible that nearly 3/4 of all the matter that exists is invisible to our telescopes, yet essential for galaxies to avoid disintegration? Dark matter is one of the greatest enigmas of modern science. It does not emit light, does not absorb radiation, nor interacts in the way everything we know does. However, without its presence, the cosmos would be a completely different, chaotic, and disorderly place, where galaxies could not hold together and the structure of the universe would collapse. Every time we look up at the night sky, what we see is barely the tip of the iceberg. The matter that shines, the one that forms stars, planets, and people, represents only a small fraction of the total. The rest is that silent and omnipresent mystery, as if the universe were held together by an invisible net of which we have barely any hints. Isn't it fascinating to think that everything we have studied and understood so far is just a tiny part of the cosmic story? The search for dark matter is not just a matter of physics or astronomy, it is also an open window to the unknown. What if dark matter hides a new physics, completely different rules than those we believe to be unbreakable? Just as ancient navigators sensed the existence of distant continents by the currents of the sea, scientists deduce dark matter from the traces it leaves in gravity and in the evolution of the universe. Every clue, every anomaly, and every small discovery brings us a little closer to understanding what the universe is really made of. In the end, dark matter teaches us humility. It reminds us that no matter how much we think we know, the universe still holds deep and complex secrets. Who are we in this vast ocean of the unknown? What other surprises await us when we manage to decipher this invisible puzzle? The mystery of dark matter challenges us to look beyond, to question our certainties, and to keep curiosity alive. Because as long as the unknown exists, the human drive to explore, discover, and marvel at the greatness of the cosmos will endure.